Hello and welcome to this week's video lesson in chemistry. We're still looking at Unit 3, Chemistry and Society. So far we've covered plastics and fertilisers, and this week we're looking at nuclear chemistry. Metals we will work on when we're back in class, and we'll do an overview of chemical analysis back in class as well. So our starter question this week is related to the prior knowledge required to do the nuclear chemistry topic. So I'd like you to think about what information is given by the mass number of an element, what information is given by the atomic number of an element, and I'd like you to draw a simple diagram to represent an atom of carbon with a mass number of 12, which can also be written using the Nuclei Notation 12(6)C. And I'd like you to label all of the subatomic particles in that atom. Pause the video now and try the starter question. So hopefully you've remembered this is key information. The mass number of an atom or an element tells you the number of protons plus the number of neutrons, or it's equal to the number of protons plus the number of neutrons. So the mass number tells you the total number of protons and neutrons. The atomic number of an element is equal to the number of protons, and it's also equal to the number of electrons in a neutral atom. If you are asked to draw an atom of carbon with a mass number of 12, the atomic number, remember, gives you the number of protons and electrons, so you should have drawn 6 protons in this middle bit of the atom called the nucleus, and the 6 electrons are arranged 2 in the first shell and 4 in the second shell. The mass number of this carbon atom is 12, and that means that there are 12 protons and neutrons altogether. If there are 6 protons, that means there must be 6 neutrons as well to give 12. To work out the number of neutrons, remember you can do the mass number, which is the top number, take away the bottom number. So 12 take away 6 gives you 6 neutrons. Okay, so really important that we're remembering atomic structure for this topic. Protons and neutrons are found in the nucleus, and they also have a mass of 1, and protons have a positive charge, neutrons have no charge. Electrons are found in the electron shells, and electrons have a negative charge, but very little or to no mass. So let's get started on nuclear chemistry. I'd like you to begin by just thinking about what you think this topic might be all about. So this symbol here gives you a clue, as does the word nuclear. Okay, so you might recognise this symbol as the hazard symbol for something that's radioactive. So nuclear chemistry is all about studying radioactive atoms, and it's called nuclear chemistry because this chemistry is all to do with the chemistry of the atomic nucleus. This chemistry relates to other areas you might have heard of, such as nuclear weapons and nuclear power. So we're going to cover this topic in 2 parts in this video, and then a little bit more at a later stage in class. So the first part of this video is going to look at the different types of radiation. So when we talk about something being radioactive, it's radioactive because it emits radiation. So we're going to be looking at why some elements are radioactive. We're going to be looking at 3 types of radiation: alpha, beta and gamma, and we're going to be learning about what these are and how they can be stopped and how far they can travel. And then the second part of this lesson, we're going to look at nuclear equations. That's also going to focus on these different types of radiation. And then there are aspects of this topic to do with something called half-life and the uses of radioisotopes, and we're going to cover those at a later stage. So let's get started looking at why some isotopes are radioactive and what these different types of radiation are. So the first thing I'd like you to do is watch this clip on how the elements are made. This is a really good background knowledge to help you to understand why some elements are radioactive. It's very interesting, so please make sure you pause this video. I'll put a link to this clip in the description to this video, so you can click on that and watch it before you go any further. Okay, so if you're looking at this slide, I'm hoping you've watched the video about how the elements are formed, and you should have learned that elements are formed by nuclear fusion in stars and supernovae. So what we mean by nuclear fusion just means bringing together. So everything starts with hydrogen, which just has 1 proton, and that then fuses to become helium, which has 2 protons and 2 neutrons, and all of the heavier elements are built by the nucleus or the nuclei of other elements basically just getting smashed together. So heavier elements are formed by other smaller elements coming together. And you should remember that the nucleus contains protons and neutrons, so basically we make heavier elements by just mashing together lots of protons and neutrons, and what we find is that only certain proton to neutron ratios leads to a stable atomic nucleus. So that's what's shown in this graph here. So this graph is what's known as the nuclear stability curve. And what you can see is that this dark line represents stable proton to neutron ratios. So for example, if we have 20 protons, a nucleus with 20 protons would be stable. The black line represents the stable nuclei. That would be stable with about 20 neutrons. So that's a 1-to-1 ratio. If we go a little bit higher, if we've got 40 protons in our atom, that's going to only be stable when it's got about 50 neutrons, and anything higher or lower than that will be an unstable atomic nucleus. So just to check that you've got the hang of this, take a look at the graph and see if you can figure out how many neutrons are needed for a stable atom, first of all with 10 protons and secondly with 60 protons. You don't need to write it down, just have a think. Okay, hopefully you're thinking, well, if there's 10 protons, then we got to the dark line here, and 10 protons would be stable with 10 neutrons. If we've got 60 protons in our nucleus though, if we find where that meets the dark line here, which is for stable nuclei, we need about 85 roughly neutrons for a nucleus with 60 protons. And like I say, anything around that is an unstable nucleus, and as you can see from this graph, unstable nuclei are the ones that are radioactive. So we're going to write that down in the next slide. Okay, so atoms with unstable nuclei are also called radioisotopes because they are radioactive, and they become more stable by giving out alpha, beta or gamma radiation. Make sure you write down the information on this slide, and then we're going to go on to look at the different types of radiation and what they are. So for each type of radiation, alpha, beta and gamma, we've got quite a lot of information that we're going to learn and that you need to know about it. So to make your life a little bit easier, I'd like you to write down this table into your notes so that you can record the information as we learn about each type of radiation. So you're going to learn the symbol, what the radiation is, its charge, atomic mass, speed, distance travelled in air, what it's stopped by, and the ionizing power. So we'll look at these first 5 first of all, and we'll do a little overview of the table, so don't worry too much if you can't get this down while we're talking about it, but make sure you copy the table down for now. Okay, so pause the video if you need to, and then we'll start on alpha radiation. So alpha particles, alpha has radiation has this symbol here. I think of it as a bit like a little fish. This is the lowercase symbol for the Greek letter alpha. And we've said that atoms emit radiation when they're unstable, and they emit radiation from the nucleus to try and become more stable by changing their proton to neutron ratio. So alpha particles are a type of radiation emitted from the nucleus of large atoms. And what an alpha particle is it's 2 protons and 2 neutrons, which basically means it's the same as a helium nucleus. So helium has an atomic number of 2, meaning it's got 2 protons. So if we've got a particle with 2 protons, that is a helium nucleus. So the alpha particle is effectively a little chunk of the nucleus breaking away, and that chunk, like I say, contains 2 protons and 2 neutrons, and is could also be referred to as a helium nucleus. So the alpha particles move at relatively slow speeds, and over time most very unstable nuclei will emit several alpha particles, and then gradually they'll achieve a state where they become a stable nucleus. So what do you think happens to the mass and atomic number of the nucleus after this alpha particle leaves? Well, the alpha particle has a mass of 4, so if it's leaving, the mass of the nucleus is going to decrease by 4. The alpha particle also has 2 protons, so if it leaves, the nucleus will have 2 fewer protons, so the atomic number of the nucleus is actually going to change. This is pretty crazy, because actually what this means is that one element is going to change into a different element, because remember, each element has a unique atomic number. We're going to look at this in more detail when we look at the nuclear equations, but I think that fact is quite amazing, that elements can actually change from one into another by emission of radiation. So the next thing we're going to look at is beta particles. So beta particles again have this symbol here, it's the Greek letter beta, and beta particles are also emitted from the nucleus. And what a beta particle is it's a single electron leaving the nucleus. So do you see a problem with that? Hopefully you do. Well, the problem is that there aren't any electrons in the nucleus, right? The electrons orbit the nucleus, so this is strange. The explanation for beta radiation, if we were to go into the detail, it's quite advanced physics, but the basics of what happens is a neutron in the nucleus changes into a proton and an electron. And the electron is then fired out of the nucleus as a beta particle. So beta particles are quite fast moving electrons, they're quite fast compared to alpha particles. And like I say, they're formed by a neutron in the nucleus changing into a proton and an electron. Again, we'll look at this in more detail in nuclear equations. So what do you think happens to the mass and atomic number of the nucleus after the beta particle leaves? Well, hopefully you remember that electrons have almost no mass, and the mass of the nucleus isn't going to change, but if we've got a neutron changing into a proton and the beta particle, the number of protons in the nucleus is going to increase by 1, so the atomic number is going to increase by 1. Again, the actual element that this atom is going to change. Amazing. Okay, so let's look at the final type of radiation, which is gamma radiation. Gamma has this symbol here, again Greek letter gamma lowercase, and gamma radiation is an electromagnetic wave which is released from the nucleus. So for those of you who have done physics, you will probably remember this, you'll probably know this in a lot of depth, but if you don't do physics, hopefully you remember maybe from first and second year that visible light, also ultraviolet light, infrared, x-rays, microwaves, radio waves, these are all types of electromagnetic radiation, or electromagnetic waves, and all of these waves travel at the speed of light. So gamma radiation is the highest energy form of electromagnetic radiation. X-rays are pretty high energy, but gamma is even higher energy. So as I say, they move at the speed of light, and basically gamma radiation is just a way of the nucleus releasing energy. So what do you think happens to the nucleus after the gamma radiation leaves? Well, it's not going to change, the number of protons and neutrons won't change this time, but like I say, the nucleus will just have a lower energy as it's releasing some high energy radiation. So this is a little summary of what we should have learned so far. So we've got our symbols there, which I hope you managed to get down. Alpha particles are a helium nucleus, or you could have written 2 protons and 2 electrons, but it is worth mentioning that it's a helium nucleus. Beta is a high energy electron, gamma a high energy electromagnetic wave. The charge, I'm not sure if you've got this one down, so an alpha particle, because it's just the nucleus of a helium atom, it doesn't have any electrons, each proton is positively charged and there are 2 of them, so the alpha particle is going to be 2 positive. Beta particles are electrons, so they will have a charge of 1 negative, and electromagnetic waves do not have a charge, so the gamma rays will have no charge. The atomic mass, hopefully you might have got that down for alpha, that was 4. Electrons, remember, have a mass of almost nothing, and electromagnetic waves also have no mass. In terms of the speed, we don't need to give a number, we just need to say relatively, so alpha particles are slow, beta particles are fast, but gamma rays are the fastest and they travel at the speed of light. So that gives you an overview of these different types of radiation and what they are. Remember, all of these types of radiation are ways that unstable nuclei can try to become more stable. We could also say the unstable nuclei decay to become more stable, and we talk about alpha decay, beta decay, and gamma decay. So that's something that's a phrase that will come up more when we look at nuclear equations. So now we're going to look at some other properties. So we're going to look at the penetration power, or what these different types of radiation can be stopped by, because radiation can be dangerous. We'll look at that in a little minute, and it's important for us to know how far these different types of radiation can travel and what they're stopped by. So Gamma radiation can travel the furthest. It takes thick lead or concrete to reduce gamma radiation. Beta is the next furthest, so beta particles can travel through very thin films and paper, but they're stopped by thin aluminium. Alpha particles can travel through the thinnest of films. Mica is just a material that can be made into a very thin film, but alpha particles are stopped by paper or skin. We'll fill that in the table in a wee minute. So, here's the table here. So, the other thing to fill in is the distance they can travel in air. I didn't have that on the previous slide, but the alpha particles can travel a few centimetres in air. So they can hardly travel at all, a few centimetres in air, and they are stopped by paper or skin. Beta radiation can travel a metre or two in air, and it's stopped by thin aluminium. Gamma rays can travel very far in air, just like light. Light reaches us from the sun. Gamma rays can travel very far, and you have to have thick lead or concrete to stop gamma rays. So, last thing we'll look at in this part of the video is we'll talk a little bit about the danger associated with radiation. So, radiation can be dangerous. It can damage the cells that make up the human body. Low levels of radiation are not dangerous, but medium levels can lead to sickness, headaches, and vomiting. And high levels of radiation can kill you by causing damage to your internal organs, and it's extremely difficult to treat this radiation exposure. If you're exposed to low to medium levels but over a long time, this can also cause cancer. So radiation can be worrying, but also it's something that we come across in everyday life. So there are many sources of background radiation. And these are things that humans are exposed to all the time. So we've got cosmic rays coming from the sun, food and drink, and rocks and soil. All of these contain very small amounts of radioactive isotopes. I think a good example is the potassium in bananas, but bananas are quite rich in potassium, and some of those potassium atoms are radioactive. But it's at a low level, which even over a long time is not enough to cause us any significant damage. So the danger level depends on the exposure, so how much you're exposed to and for how long. Physicists, if you do physics, you'll look at how you measure the quantity of radiation. That's not something that we'll go into here. And also depends on the type of radiation. So the different types of radiation have different danger levels, and we'll look at that now. So the harm caused by radiation is caused by ionization in the cells in the body. So hopefully you remember that ions are charged particles, and ionization occurs when the electrons are removed from an atom. So if you think about these radioactive particles, these alpha or beta particles or gamma rays being kind of ejected, thrown out of atoms, they can then strip electrons from the matter that they pass through, leaving ions behind. It's a bit like if you imagine firing a snooker ball at the group of other snooker balls. Some of them can be knocked out of place, so that's what happens when something like an alpha particle hits the electrons in another atom. So charged particles will cause more ionization than neutral ones, and the larger particles are more likely to collide with electrons. So a little bit of problem solving here. Based on these two pieces of information, can you rank the ionization ability of alpha, beta and gamma radiation as high, medium or low? So if you want to, you can have a think about that, pause the video and then see if you're right in the next slide. Okay, so ionizing power alpha, well, they're highly charged and quite big, because they're made of protons and neutrons, which are relatively heavy compared to electrons and waves, so they have high powers of ionization. So alpha, although it can't travel very far, if it does come into contact with you, it's quite dangerous. It has a high ionizing power. Beta radiation has a medium ionizing power, and gamma rays, because they are not charged and they do not have any mass, they have quite a low ionizing power, so they can travel the furthest but are less dangerous when they come into contact with you. So just an example of how dangerous alpha radiation is if it does come into contact with you. You guys, this happened quite a number of years ago, you guys probably haven't heard of it, but there was a famous case in the UK where Alexander Litvinenko died due to poisoning by polonium-210, which is a source of alpha radiation. So there's a little bit of information about him on this slide. He was a Russian defector, and although no charges, according to Wikipedia, no charges were ever laid in the case, but strong evidence suggests Russian state involvement in his murder, and it's one of the only cases of murder by poisoning with this source of alpha radiation. So what happens is, whilst alpha, if I had an alpha source in the room with me, if it was far enough away from me, I wouldn't have to worry, because it can only travel a few centimetres, but he was given something which meant that he ingested the alpha radiation, so it was attacking his body from the inside, which caused serious harm. So make sure you've got this table written down, and this is information that you need to learn about the different types of radiation. The last thing we'll look at in this part is just about what happens if you put these different types of radiation in an electric field. So this basically just illustrates the charge. So remember, opposite charges attract. So beta particles which are negative will be attracted to the positive plate if they're put in an electric field. Gamma rays will pass straight through because they have no charge, and alpha particles will be deflected towards the negative side because they are positive and opposite charges attract. You don't need to copy down both diagrams, but make sure, I would say, copy down the top diagram here. Another thing that's worth noting, why do you think the beta particles, these are deflected slightly more than the alpha particles? Can you think of any reason why that might be? Well, so I'm not sure what you've come up with, but interestingly, because the beta particles are so light, they are deflected more easily, whereas the alpha particles, which are very heavy, don't get deflected as much. So you can think of it as a bit like a little canoe in the water compared to a big tanker. The tanker is going to keep moving and not go very much off course, whereas if there was a high wind, the light little canoe would be blown right off course. So that's why the beta particle gets deflected more. So we should have, so far we've covered some information about the different types of radiation and how far they can travel and their behaviour in an electric field. I would recommend that you pause this video now before continuing with the second part of the lesson this week. Okay, so this is part 2 of this week's lesson on nuclear chemistry, and in this part we're going to look at nuclear equations. So like I mentioned, hopefully you've had a little break since doing the first part of this week's lesson, because you're going to need to think a little bit more carefully for this part. So we're going to learn about how to represent alpha, beta and gamma radiation in nuclear equations. We're going to learn about how to represent protons, neutrons, probably not electrons actually, but we're going to learn about how to represent protons and neutrons in nuclear equations, and we're going to look at writing nuclear equations for alpha and beta decay. I'm going to switch over to doing this on paper to help to show you how to write the equations. So in this section of the video we're going to look at nuclear equations. You'll need your periodic table so that you can find the atomic number for the different elements. So this is one of the few times in chemistry where we'll probably look at some of the elements with higher atomic numbers. So you're unlikely to remember the symbols for these different elements, so make sure you've got the periodic table handy. So as usual, I'm going to go through some examples and then I'm going to give you some practice questions. So the first thing to say about nuclear equations is that in a nuclear equation, all particles are represented using Nuclei Notation. We will not show charges, however. So just as a wee reminder, your Nuclei Notation is where we have the symbol for an element or particle. So we're going to look at how to represent particles in a minute. The number to the top left is always going to be the mass number, and the number to the bottom left is always going to be the atomic number. Occasionally, especially for elements, you might not see the atomic number written down, because if we have the symbol for an element, as long as we've got the periodic table, which as chemists we always should, we can find the atomic number from the symbol. So if we have gadolinium here, Gd, as the symbol, then we know the atomic number must be 64 from the periodic table. So first thing is going to be to write down the Nuclei Notation for some things you might not know about already. So we're going to write down the Nuclei Notation for a proton. So a proton, remember, has a mass number of 1, and a proton, if it was a single proton on its own, it would also be worth an atomic number of 1, because a hydrogen, which has 1 proton, has an atomic number of 1. So the symbol for a proton is going to be 1, 1p. And then we're going to think about the symbol for a neutron. So the letter for a neutron is N. So can you remember what the mass of a neutron is? Okay, well, the mass of a neutron is 1, but neutrons aren't associated with atomic number, so neutrons we would give an atomic number of 0. So that's the symbol for a neutron using Nuclei notation. Okay, and then we're going to look at an alpha particle and a beta particle as well. So an alpha particle, remember, is effectively a helium nucleus. It has a mass number of 4 and 2 protons, so an atomic number of 2. And we're going to give it the symbol He. So that's your alpha particle. And that's the same nuclide notation as you would use for an isotope of helium as well, because remember, alpha is just a helium nucleus. And then for our beta particle, our beta particle, remember, is a fast-moving electron ejected from the nucleus when a neutron changes into a proton and an electron. So what's the mass of an electron? Hopefully you're thinking 0. So the beta particle has a mass number of 0. And then because a neutron, I'm just gonna do this just now. So we give a beta particle an atomic number of -1, and actually I'm going to explain that at a later stage when we look at some examples. So just for now, just make sure you've got the notation for a beta particle written down. So the reason that the beta particle has an atomic number of -1 is to do with the next little bit that we're going to write down. So when we're writing a nuclear equation, so in a nuclear equation, make sure you're writing down this at the same time. Really the mass numbers. Okay, so in a nuclear equation, the mass numbers and atomic numbers must balance on both sides of the arrow. And we'll just look at an example straight away of this. So we're going to look at an example. And the first example we're going to look at is the alpha decay of polonium-210. So 210 PO, and then the atomic number for polonium we can find on the periodic table, 94. Oh, hold on, that's plutonium, not polonium. There we go, 84 polonium. Okay, so like I say, we can also say that, so 210 is just one of the isotopes of polonium, always has an atomic number of 84, could have different numbers of neutrons. 210 is just one of the isotopes, but we call that polonium 210, so that's just another way of saying it. So, if it's the alpha decay of this isotope is going to be effectively the reactant, so that gets written on the left-hand side. So we've got 210 polonium 84. Now, in many nuclear equations, or certainly in nuclear decay, there tends to only be one reactant, because that is then decaying into the different products. So if it's alpha decay, one of the products, and I'm going to leave a space, and I'm going to write this as the second product. One of the products is going to be an alpha particle. Okay, and then remember, if the nucleus is losing an alpha particle, the mass number of the nucleus is going to decrease by 4. So 210 take away 4 gives us 206, and the atomic number is going to decrease by 2 because there are 2 protons being lost from the nucleus. So that's what I mean by, in a nuclear equation, the mass numbers and atomic numbers must balance on both sides of the arrow. So on the left hand side of the arrow here, we've got a mass number of 210. So the total of both mass numbers in the product on this side must add up to 210, because otherwise we would have lost a proton or a neutron. So 206 plus 4 does give us the 210. And equally, the atomic numbers must balance, so 84 is equal to 82 plus 2. So we're happy that that balances now. I've written the mass number and the atomic number nice and easy. As long as you can add and take away, then that should be fine, although obviously it's easy to make silly mistakes sometimes with that. And then we just have to find out what element it is. So we're looking for something with an atomic number of 82 in the periodic table. So these are in order. So here we go. Lead has an atomic number of 82, so we're going to give it the symbol PB. And from this process, from working out the mass number and atomic number of the product when polonium 210 undergoes alpha decay, we can work out that the element produced from that is lead. So I think I mentioned this already. I think that's quite fascinating, how we can get one element literally changing into another. The chemical properties of this will be completely different once it becomes lead. Okay, so the second example that we're going to look at is a beta decay example this time. And we're going to look at the beta decay of an isotope of hydrogen called tritium. So that's an atom of hydrogen with a mass number of 3. So normally hydrogen is just 1 proton, and so it just has a mass number of 1. That's an ordinary isotope of hydrogen. So tritium is a different isotope of hydrogen. Okay, so again, because this is a decay equation, we're going to only have one reactant, and we're looking at the beta decay of this isotope of hydrogen. So this is going to be our reactant. One of our products is going to be a beta particle. So remember, the symbol for the beta particle is given there. And again, I'm going to write the particle, the radiation on the as the second product, just sort of convention. So if you can remember the symbol for a beta particle and an alpha particle, then you can work out any other aspect of a nuclear equation just by remembering that the atomic number and mass number, atomic numbers and mass numbers have to balance. And that's what I'm going to do here. So the mass numbers have to balance. We've got a 3 and we've got a 0. So the mass number for this other particle must be 3. And the atomic numbers also have to balance. So I've got to have, so something, basically I could make like almost like a little algebra equation. So my total atomic numbers on this side have to equal 1. So if I give this the symbol x, I've got x plus minus 1 equals 1. So remember, a plus and a negative can't make a negative. So x minus 1 equals 1. If I add 1 to both sides, x equals 2. So if you can't work out in your head, just make yourself a little sum up. So my atomic number here is going to be a 2. And that tells me that my product is going to be helium, because I have an atomic number of 2. Okay, so hopefully this makes sense in the context of what a beta particle is. So when a beta particle is emitted, a neutron turns into a proton and an electron. So the mass number of the nucleus should stay the same, but because a neutron is turning into a proton, the atomic number will increase by 1, and that effectively means that during beta decay, so this is something that's worth considering, during beta decay, the element that is involved in the decay will just move along 1 in the periodic table. So for example, beta decay of carbon would result in a nitrogen atom being formed. So we just move along 1 in the periodic table. I don't think you need to write that down in your notes unless you really want to, but it's a wee fact worth remembering. Similarly, with alpha decay, we're losing 2 protons and we're just going to move back 2. So alpha decay of polonium moved us back to lead. Maybe worth writing that down actually. Okay, so alpha decay we can see the element moves back 2 and beta decay, and this is in the periodic table. The element moves on 1. In PT, periodic table. Okay, so you can write that down if you want. Okay, so the third example that we're going to look at is what is the product of this neutron capture process? So this is something we haven't come across. You don't need to know about it. It's not in the course specification, but it could come up as problem solving. So neutron capture is basically just when we bombard a nucleus with neutrons, and some of those neutrons can end up getting stuck onto the nucleus. So this is a way in which some radioisotopes are artificially produced. So it's really a problem solving question, and like I say, all you need to remember again is that the sum of the atomic number, mass numbers, and the sum of the atomic numbers on both sides must be equal. So if you've just got the two products and you're looking for the two reactants and you're looking for the final product, it's nice and easy because we just need to add up these numbers. So 9 plus 1 is 10, 5 plus 0 is 5, and that means if it's got the same atomic number, that means it's still going to be boron. And if we think about it, if we've captured a neutron, we're not changing the number of protons, we're not changing the element, we're just making a different isotope of boron. So the new isotope that we're making is boron 10. Okay, so again we've got 3 practice questions. Question 1, write an equation for the beta decay of carbon 14. Question 2, write an equation for the alpha decay of radium-226. And question 3, we're given a nuclear equation here and you have to identify R. Make sure you pause the video before listening to me go through the answers to these. Okay, so here are our answers here. Question 1, hopefully that was reasonably easy. So once we've written the Nuclei Notation for a beta particle, we just need to remember that the mass number doesn't change, so we've still got 14. The atomic number increases by 1, and then that balances out because 7 plus minus 1 is 6. 7 minus 1 is 6. And once we've got the atomic number 7, we can look for the symbol in the periodic table, so that's nitrogen produced by the beta decay of carbon. Question 2, the alpha decay of 226 radium. Now I was a little bit naughty here and I didn't give you the atomic number, but you should have been able to look up the atomic number for radium in the periodic table, so that's where I got the 88 from. So you just find Ra in the periodic table and it's got an atomic number of 88. So when I'm doing my nuclear equation, I've got my mass number and atomic number. It's alpha decay, so I'm losing 42 He. I'm losing an alpha particle. My atomic number is going down by 2. Mass number is going down by 4 in the product nucleus, and therefore if it's got the atomic number 86, again you're just looking for atomic number 86 in the periodic table, which is over here, and that tells us the product is radon. Okay, and then the final one, the R is 42He. So this is again just a problem solving question based on the fact that the total mass number and total atomic number on each side must be equal. So 3 plus something must be the same as 6 plus 1. So 3 plus something must be the same as 7. So that something must be a 4. So the mass number of R must be 4. The atomic number of R, well, we've got a 3 and a 0, so we've got 3 on this side, only 1 on this side, so 1 plus something equals 3, that must be 2. And if it's got an atomic number of 2 from the periodic table, it must be helium. Okay, I'm just going to conclude this video by a quick recap of the learning intentions. So we were looking at nuclear equations, and those of you with good attention to detail might have noticed that we forgot a couple of these learning intentions. Now, these were in here because technically they are in the course specification, but actually they're not necessary to know. They will never come up. So we won't need to know how to represent gamma radiation in nuclear equations. So we should by now know how to represent alpha and beta radiation in nuclear equations. And we should also know how to represent protons and neutrons in nuclear equations, but again, electrons is never going to come up. The only context in which we represent an electron is in the context of beta decay, so as long as you know how to represent beta decay, then that's absolutely fine. So as long as we can write nuclear equations for alpha and beta decay and know how to represent protons and neutrons, that's absolutely fine for this section. Remember, you also need to know the information from part 1 of the video, so we need to know why some isotopes are radioactive, what alpha, beta and gamma radiation is, and a few of their properties, so their charge, how far they can travel in air, and what they can be stopped by. Thanks for listening to this video. If you think you need any more practice of this topic, as usual, please go to the BBC Bite Size section or the Scholar section and have a go at the questions on there.